In this video, I'm going to introduce you to sum and difference formulas. And these formulas are mainly used for finding exact values of trig functions that we don't have on our unit circle. And we can also use them to prove identities and solve equations by making substitutions. So these are our sum and difference formulas right here. In subsequent videos, I'm going to talk to you about half angle formulas, double angle formulas, sum and product formulas as well. And like I said, all of these formulas can be used to make substitutions to prove identities, solve equations, or to evaluate trig functions that we don't have already derived on our unit circle. And so for the sum and difference formulas, we're going to use two angles. We're going to break it up either into a sum or a difference using values on our unit circle that we already know to evaluate a trig function of an angle that we don't have on the unit circle. In example A, we have the sine of 75. And if I want to find the exact value of the sine of 75, I don't have that derived on my unit circle. But I can break it up into angles that we are familiar with. So I'm going to rewrite sine of 75 as the sine of 30 degrees plus 45 degrees. These we do know, and we do have those on our unit circle. Now I can think of this as my S, and this is my T, and I can rewrite this using the formula above. So using our formula up here, the very first line, this is the sine of S plus T. I'm thinking of 30 degrees as S, 45 degrees as T, and I'm going to rewrite it as sine S cosine T plus cosine S sine T. So I have sine S cosine T plus cosine S sine T. And we said S is 30 degrees and T is 45 degrees. Now if I look at my unit circle, I know that the sine of 30 degrees is 1/2, so I'm going to replace sine of 30 degrees with 1/2. Cosine of 45 degrees is the square root of 2 over 2. Cosine of 30 degrees is the square root of 3 over 2. And sine of 45 degrees is the square root of 2 over 2. When I multiply 1/2 times the square root of 2 over 2, I get the square root of 2 over 4 plus, and when I multiply the square root of 3 times the square root of 2, I get the square root of 6 over 4. And then because these are already common denominators, I can combine them without having to do anything else. And I get the square root of 2 plus the square root of 6 all over 4. So this is the exact value of the sine of 75 degrees. If I scroll down to example B, I am going to rewrite tangent of negative pi over 12 as pi over 4 minus pi over 3. And I made sure that I used angles that I had on my unit circle. Now if I scroll back up, I'm going to look for tangent with the difference of angles. I'm going to look for the formula for tangent that has the difference of angles. That's this one right here. Tangent of S minus T. So I'm going to think of pi over 4 as my S and pi over 3 as my T. And I'm going to rewrite this as tangent S minus tangent T all over 1 plus tangent S times tangent T. Now because we're identifying pi over 4 as S, I'm going to write that as tangent of pi over 4 minus tangent of t. T is pi over 3. So that's the tangent of pi over 3 all over 1 plus tangent of pi over 4 times tangent of pi over 3. Now we know what tangent of pi over 4 is. That's the value of y over x at the angle pi over 4 radians. So that would be 1 minus tangent of pi over 3 is going to be the square root of 3 all over 1 plus tangent of pi over 4 we said is 1, and tangent of pi over 3, when I multiply those, that gives me the square root of 3. So when I completely clean this up and I multiply the 1 times the square root of 3, I get that the tangent of negative pi over 12 is exactly 1 minus the square root of 3 over 1 plus the square root of 3. The next example, I can rewrite 105 degrees as 150 degrees minus 45 degrees. I have both of these angles on my unit circle. Now there may be another way to write this. So as long as it adds up or you subtract and take the difference and you get 105, you can write it however you want. You just want to make sure that you're picking angles that are from the unit circle. Now, if I have the difference with cosine, my formula, if you look back up in the shaded box, it's cosine of s, cosine of t, plus sine of s times sine of t. So s is 150, so I have cosine of 150 times cosine of t, which is 45, plus sine of s, which is 150, and sine of t, t is 45. Okay, now if I look at the unit circle, the cosine of 150 degrees is negative the square root of 3 over 2. Cosine of 45 is the square root of 2 over 2. Sine of 150 is 1/2. And sine of 45 degrees is the square root of 2 over 2. Now when I multiply negative square root of 3 over 2 times square root of 2 over 2, that gives me negative square root of 6 over 4 plus, and then I have 1/2 times the square root of 2 over 2. That gives me the square root of 2 over 4. Since they have a common denominator, I can just go ahead and add them. So I get negative square root of 6 plus the square root of 2 all over 4. So this is my exact value for cosine of 105 degrees. Okay, example D, I can write sine of 11 pi over 12 as sine of 2 pi over 3 plus pi over 4. So that formula would be, if this is my s and that's my t, my formula is going to be sine s times cosine t plus cosine s times sine of t. And now I'm just going to substitute in my values for s and t. So I have sine of 2 pi over 3 times cosine pi over 4 plus cosine of 2 pi over 3 times sine of pi over 4. So now I just have to look these values up on the unit circle if you don't already have them memorized. The sine of 2 pi over 3 would be the square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Cosine of 2 pi over 3 would be negative 1/2. And sine of pi over 4 is the square root of 2 over 2. Now, when I multiply the square root of 3 over 2 times the square root of 2 over 2, that gives me the square root of 6 over 4. And when I multiply negative 1/2 times the square root of 2 over 2, I get negative square root of 2 over 4. And when I combine those, because I have a common denominator, I get the square root of 6 minus the square root of 2 all over 4. So this is my final answer for my exact value for sine of 11 pi over 12. Now, example E is given to us slightly differently. Instead of listing it out as an angle in degrees or radians, it's giving us the angle as an inverse trig function. So I want to think of this as my angle S, and this as my angle T. And my formula for cosine of S plus T would be cosine of S times cosine of T minus sine of S times sine of T. We're not given what that actual angle is as far as the number of degrees or the number of radians. We can come up with a triangle and find out what the values of our cosine S, cosine T, sine S, and sine T values are. So we're doing this a little bit differently because of the information that's provided to us. So I'm going to create triangles so I can identify the values that I need in this formula. So this is going to be angle S, and I'll label this as angle T. For angle S, we have inverse sine of the square root of 3 over 2. Now, sine is opposite over hypotenuse. So the opposite side of S would be the square root of 3, which would be that side there, and then the hypotenuse would be 2. If I solve for my last side, I would have a 1 here using Pythagorean theorem. I have cotangent as the square root of 3, and cotangent is adjacent over opposite. So I'm going to have this as the square root of 3, this as 1, and then using Pythagorean theorem, I'm going to have that the hypotenuse is 2. So now I have my triangle set up so that I can identify the trig functions for S and T. So the cosine of S means I'm going to be looking at the triangle with the angle labeled as S. Cosine is adjacent over hypotenuse. So adjacent over hypotenuse would be 1/2. Cosine of T means I'm looking at the triangle labeled with the angle T. And again, cosine is adjacent over hypotenuse. So that's going to be the square root of 3 over 2. For sine of S, that means I'm going back to the triangle with the angle labeled as S. And the sine of S is going to be the opposite over hypotenuse, which would be the square root of 3 over 2. And sine of T means now I'm going back to the triangle with the angle labeled as T. And I'm going to use the opposite over the hypotenuse, which is 1/2. And now I'm going to multiply through. So I have 1/2 times the square root of 3 over 2. That gives me the square root of 3 over 4 minus, and then I'm going to get the same thing here, the square root of 3 over 4. So in this case, the cosine of those two angles added together is just 0. Now this would be a really great quiz question or a really good exam question because it forces you to go back and review inverse trig functions. It forces you to remember the Pythagorean theorem and set up your triangles. It forces you to remember your trig ratios. and you're doing the sum and difference formula all at the same time. So this incorporates a lot of ideas. So this would be a really good exam or quiz question. So in the next several examples, it's asking you to write each expression as a single trig function. So it's asking you to work backwards of what we just did. So first, identify your angles, S and T. So let's let S be 3 pi over 7. And let's let T be 2 pi over 21. So that means I'm looking for the formula where we have cosine of S, cosine of T, plus sine of S, sine of T. And we want to work backwards. So if I look up in my shaded box at the beginning of the notes, that would be this identity right here. The cosine of S minus T is cosine S, cosine T, plus sine S, sine T. We're going to write it. We're working backwards. We have this part here, and we're going to write it as cosine of S minus T. So cosine of S minus T would be cosine of 3 pi over 7 minus 2 pi over 21. This is my S, that's my T. Now we can combine those. If I make a common denominator, if I multiply the 3 pi over 7 on the top and the bottom by 3, that gives me 9 pi over 21 minus 2 pi over 21. And then I can write my final answer as the cosine of 7 pi over 21, which would be pi over 3. So that big mess up here is equivalent to cosine of pi over 3. Okay, now we're going to do the same thing with example B. I'm going to identify 8S as S and 7x as angle T. So I'm looking for sine S, cosine T, plus cosine S, sine T. And if I look back up in the shaded blue box where we have all of our formulas, that would be the formula for sine of S plus T. And if I write that as sine, S is 8x, T is 7x, so I can rewrite that as sine of 15x. So this is equivalent to sine 8x cosine 7x plus cosine 8x sine 7x. Okay, one last one. I'm going to identify this as S and 4x as T. So I'm looking for sine of S, cosine of T, minus cosine of S, sine of T. And if you look up in that shaded box, that is going to be the formula for sine of S minus T. So when I replace S with 7x and T with 4x, I can rewrite that whole big mass as sine of 3x. Now in this example here, again, we're given our angles as an inverse function. So we're going to have to set up our triangles in order to write this expression in terms of x and y only. So I'm going to label sine inverse of x as angle S and tangent inverse of y as angle T. And so this is giving me cosine of S minus T, and the formula for that is cosine of S, cosine of T, plus sine of S, sine of T. So I want to write all of this big mess in terms of x and y only. And I'm going to do that by setting up my triangles and substituting all of those trig values with our ratios. So our first triangle, I'll label that as angle S. And we have our second triangle, and I'll label this angle T. So if I look up here at angle S, this is telling me that the sine of S is x. And I can write that as over 1. And since sine is opposite over hypotenuse, I have x as the opposite side of S and 1 as the hypotenuse. Then I've got to find the other leg of that triangle using Pythagorean theorem. So when I do that, I'm going to get 1 minus x squared as my other leg. Okay, now for angle T, that's this angle here, it's telling us that the tangent of angle T is equal to y, and I can write that over 1. And tangent is opposite over adjacent. So I'm going to label my opposite and adjacent sides with y and 1. And then I can find my hypotenuse using Pythagorean theorem, which I would get y squared plus 1. Now I have all the information I need. So I'm going to go back over here and I'm going to find the cosine of angle S. So I'm going to look at the triangle with the angle S, and cosine is adjacent over hypotenuse. So that would be the square root of 1 minus x squared. Then I'm going to look for cosine T at the other triangle, because that is the angle I have labeled with T. Cosine of angle T is adjacent over hypotenuse, so that's going to be 1 over the square root of y squared plus 1. Now I'm looking for sine of angle S. So I'm going to be looking at angle S. The sine is opposite over hypotenuse, so that's x over 1, which is just x. And sine of t, so now I'm looking at the angle labeled t, and I'm looking at opposite over hypotenuse, so that would be y over the square root of y squared plus 1. So now I just have to multiply this out and clean it up. So for this part here, remember there's a 1 under here, even though I didn't originally put it in there. When I multiply the square root of 1 minus x squared over 1 times 1 over the square root of y squared plus 1, we are going to get the square root of 1 minus x squared all over the square root of y squared plus 1. And then for the second product, we have x times y in the numerator, and then in the denominator, we have y squared plus 1. Because there is a common denominator here, I can add them together, and I'm just going to leave it as the square root of 1 minus x squared plus xy all over the square root of y squared plus 1. So this would be our final answer. Okay, the last thing I wanted to show you, you can use some indifference formulas to prove identities or solve equations. So in a previous section, we talked about cofunction identities, and now we actually have the tools that we can prove it. So I'm going to prove to you that the cofunction identity for cotangent of pi over 2 minus u is equal to tangent u is true. And we're going to use our sum and difference formulas to do that. So if you recall, cotangent of some angle is cosine of that angle divided by sine of that angle. And so this is the angle that we're talking about right here. So I'm going to rewrite cotangent of pi over 2 minus u in terms of cosine and sine. So I'm going to write this as cosine of pi over 2 minus u all over sine of pi over 2 minus u. And then I can use the sum and difference formulas of sine and cosine and simplify it and show you that this is equivalent to tangent of the angle u. So if you scroll back up and you look at your formulas for cosine when you have the difference of angles, that's going to be, and you want to think of this as your s and your t. So I have cosine of pi over 2 times cosine of angle u plus sine of pi over 2 times sine of u. So that's my formula for cosine of s minus t. Now I'm going to use the sine formula for s minus t. So sine of pi over 2 times cosine of u minus sine of u times cosine of pi over 2. Now we're going to try to simplify this and show you that this is equal to tangent u. Any term that has cosine of pi over 2 is going to disappear because cosine of pi over 2 is 0. So this is equal to 0 and this is equal to 0. And when I take 0 times cosine of u, I get 0. So this whole thing disappears. This is equal to 0. And when I multiply that by sine of u, this whole thing disappears. So now I'm left with sine of pi over 2 times sine of u on top. And on the bottom, I'm left with sine of pi over 2 times cosine of u. Now the sine of pi over 2 is equal to 1. So this I can cross off and replace with the 1. And this I can cross off and replace with the 1. So what I'm left with is sine u, because 1 times sine u is still sine u. And then on the bottom, I'm left with cosine u, because 1 times cosine u is cosine u. And sine over cosine is tangent. So we just proved our cofunction identity for cotangent and tangent. Okay, let's prove this next identity using the difference formula for cosine. Think of this is my s and this is my t. So I have cosine of s minus t. So I'm going to rewrite cosine of x minus pi using our formula. So using the difference formula for cosine, I have cosine of s, cosine of t, plus sine of s, sine of t. And we want to show that that's equal to negative cosine x. Well, if I replace s, everywhere I see s, I'm going to replace it with x. And my t is pi. And now I can simplify and show that this is equal to negative cosine x. Cosine of pi, we know what that is. That's negative 1. So I have negative cosine x. Sine of pi is 0. And when I take 0 times sine x, this whole thing disappears because it's plus 0. And when I take negative cosine x and add 0, I certainly get negative cosine x. So this one works as well. Okay, last example that we can use sum and difference formulas to prove identities. We have tangent x minus tangent y is equal to sine of x minus y over cosine x times cosine y. Now, most of the examples we've done with identities, the left-hand side seems to be the more complicated one that we try to simplify and show that it equals to the right side. In this case, I'm going to manipulate the right-hand side using my sum and difference formulas and try to show that that's equal to the left-hand side. So I'm going to use my formula for the difference of angles for the sine function. So I'm just going to bring down tangent x minus tangent y, and I'm going to rewrite this fraction using, in the numerator, my sum and difference formula for sine. Think of x as your s and y as your t, and use your sum and difference formula for sine. So I have sine of x cosine of y minus cosine of x sine of y, and that's all over cosine x cosine y. I'm going to bring down my tangent x minus tangent y, and I'm going to use the trick that I break up my fraction into two different fractions and then simplify. So I'm going to have sine of x cosine of y all over cosine of x cosine y, and I'm going to subtract cosine x sine y all over cosine x cosine y. So I use the trick of splitting it up into two fractions. And now I can cross off what they have in common. So that's going to leave me with sine x over cosine x. And over here they have a cosine x in common that I can cross off. And that's going to leave me with a sine y over cosine y in common. And I want to show that that's equal to tangent x minus tangent y. And when we have sine over cosine, that's tangent. Again, we have sine over cosine, so this is tangent. And we just showed that tangent x minus tangent y is equivalent to sine of x minus y over cosine x cosine y using the sum and difference formulas.